Good afternoon. This is our 9th session, second module, review of basic structural analysis. So we are still doing the force methods, but we hope to complete it in this session. We will cover approximate methods of lateral load analysis, and this is in part 4 of the book on structural analysis. Now I have given you an assignment, and I'd like to help you solve this assignment. So take a look at this truss. What is the degree of indeterminacy in this truss? It's 1, right? Is it internal or external? Clearly internal. Now the problem given to you is a little more complicated. You have a cable, so it's a cable suspended truss. Now what's the degree of indeterminacy? 3? 2. See, you have an additional unknown force. What is that unknown force? The force in the cable. Okay, so you've got a degree of indeterminacy 2. So how do you solve this problem? Can you treat the cable as another truss element?
No.
Why not?
Because cable cannot take compression.
Yeah, but in this case it's obvious it's going to be in tension, so you can. Okay, so in this case you can treat the cable as another truss member. You can number it 7. So how do you go about solving this problem? Now the question asked is, analyze this truss, find the bar forces and the cable tension, plus a deflection question. Can you find the vertical deflection at, or given that the vertical deflection at C is 12 mm, find the value of EA, okay, the axial rigidity, and for the cable you are told the value of the axial rigidity is 2 times that of each bar in that truss. So let us see how we can do this problem. You need to choose 2 redundants, okay. One, clearly you can choose the cable itself, and the other one could be any bar. Let us say bar number 6, the diagonal. So you cut these 2 elements and you can number them. So let us say x1 is the unknown force in the bar number 6, and x2 is the unknown force in the cable, which is element number 7. Is it clear? Assume tension positive. You know how to solve this. There are many ways of solving it. Basically you have to invoke compatibility conditions. If you do the method of consistent deformations, you have to write it in that flexibility format, or you could use the theorem of least work. You are familiar with this, you will do it. Now this part is easy. How will you find the vertical deflection at C? You give a unit displacement at C in the same system, right? Unit force at C, unit load at C, but then that's statically indeterminate. Does it mean you have to solve that statically indeterminate problem all over again for this condition, or is there an easier way out? So this is what you would be doing, right? Solve again x1 and x2 for this problem, find the bar forces and so on, right? But that's a lot of work. Can we make it simpler? I have hinted at this when we covered the principle of virtual work, the unit load method. There is a tremendous power in that method. What is the
All this thing.
You need to analyze this truss, right? This truss is statically indeterminate. You need to solve a 2 by 2 matrix to get x1 and x2 in this part, right? What's a simple way out? Anybody? Which really reduces the problem. No, it's a mind-boggling. Yes? There are no 0 4, well those you have to do anyway, but it's indeterminate. Anybody?
You take that identity matrix.
Just go back to the principle of virtual work. What was the requirement of the force field? That it should it should be statically admissible. We are looking at that field. Is it required that that system should also be kinematically admissible? No. So can you take advantage of this? How many statically admissible force fields can you draw for this? Infinite. So choose one which is easy. What's the easiest one?
The resultant of 1 is x2 and b.
Oh, it's easy. Just assume x1 x2 to be 0, right. I mean you can choose any numbers, any combination that you want, but this, it can't be easier than this. So now you are left with finding 5 unknown bar forces, which is very easy to do, right. Then you invoke the unit load method, that is it. So this is something which most students do not know. It is a power inherent in this principle of virtual forces. Is it clear? You can do this problem? Right. Now let us look at another problem which you have in your assignment. In this problem you have a hinge, please note there is a hinge at B, there is an internal hinge at B. How do you solve this problem? The problem is you have to analyze, well you need to analyze both the arches, both are parabolic arches, you need to draw the bending moment diagram etc. for the first arch ADB, right. You do not worry about the BC arch. So how do you solve this problem? Can you simplify it? No, you have 2 arches, you learned how to solve 1 arch, right. You got 2 joined together like what are they called? What twins are they? Siamese twins, yes. So what do? You separate them, right. When you separate them, how would you separate them?
Same roller
You
support.
need to separate the 2 arches.
Give the same roller support.
Same force, same horizontal force.
Same horizontal.
You see the second arch is completely unloaded.
Yes sir, we give the horizontal force from the B.
But how do you find the horizontal? In the arch
From
problems you have studied till now, there were 2 hinged arches. That support B was a hinge support not moving. Now you have a roller there, but you have a restraint coming from the other arch. So can you separate out that first arch?
Put 2 pin supports.
No, B is still going to move. No, so how do you? But it's not.
Make a section.
It's not free to move because the other arch doesn't want to be moved. So how do you deal with this? Yeah, you said.
We
Whatever
will
method
calculate
you
the energy.
do, it's not easy. Yes, you put a spring. Wonderful. That's right. You put a spring, right? Now you can use energy method, etc., provided you can know what that spring stiffness K is. So how do you find that spring stiffness K?
Material property.
Yes,
Material property.
not displacement.
Material properties.
You take the other arch and you push it horizontally at B by some force, say F, and see how much it moves, delta. By the way, look at this arch, the vertical reactions are statically determined, right. Horizontal reaction H is not known. If that spring stiffness were to be infinity, you know how to solve the problem. If it is 0, H is going to be 0 because it is simply supported, but the value of K is going to determine the value of H, right. It will lie between these 2 bounds, 0 and the value you get when K is infinite. How do you get K? Well, take the second arch, which is the same as the first arch, and apply a force F. It is going to move, right. Can you see it moving in that picture, right. Now how do you find this delta? How do you find that? You can use any of the methods, but the easiest would be to use the energy method itself. So do you agree K is F by delta? If you use the energy method, you will find that the bending moment at any section in that arch is only due to F. So it is F into Y, it is a hogging moment minus Fy. Do you agree? And if you bring in Castigliano's theorem, delta is du star by df, right, which you can write in this form, agreed, and you need to integrate only on 1/2 because it is a symmetric arch. Now m is nothing but minus fy and dm by df will therefore be minus y. So want to take this format. Now you have to use a trick which we learnt in the last session. Yeah, you make that assumption I is equal to I naught square root of 1 plus y dash squared, and that expression will delta will now simplify. I am actually leaking out the solution to you. It will simplify to this quantity, and this quantity is a constant for the arch. You remember we found this, and that takes this value. Okay, remember it was 4 by 8 or something, so it is 8 h squared L by 15. So you got an expression for k in terms of ei naught, in terms of ei naught. Now what do? Now you come back to the original arch. How do you still solve it?
Here at B it must be equal.
Well, let us stick to the energy method, which is what we use for solving the parabolic arch. So you have to go back to the derivation of how you found capital H. How did you find it? Right, you began with complementary strain energy, but now you realize that the complementary strain energy has two components. One, that of the arch due to the bending of the arch, and the second is due to the spring. Do you agree? That is the addition term. This is how you should think, because real life problems are like this. You want to simplify it, this is how you deal with it, otherwise you have to work with both the arches. Now if you run that derivative through the second term, do you agree the spring is half h squared by k, because the force in the spring is h, you agree, and the derivative turns out to be h by k, which is nothing but the deflection in the spring, right. K you already know, so you can now use this concept and get an expression for h. So go back to the original theory, you will find when there was no spring this term was not there, ei naught by k was not there, that is k was infinity, right. So you can, I want you to derive it from first principles, you will find you can do this, and you know the denominator, you can add up this value of k here with a value that we have derived for the parabolic arch. Now it is easy to do, right. You need to first chalk out the road map given a problem and then proceed. So it is an interesting problem. So will you do this? I have given you two problems, both related to force methods. And now in this session, before we take approximate lateral load analysis, let us complete some discussions on elastic supports. Now take a look at this, it is a little complicated, we will study this in grids later, but you can always try to separate out elements, but you must put the right restraints when you separate them out. For example, if I want to separate out that cantilever AB, what should I put at B to simulate the effect of the connecting beams CBD? One spring?
Rotational spring.
Yeah, so you need to put two springs, a rotational spring and a translational spring, and you need to figure out those stiffness values, which are simply K will be, you apply a force vertically downward at B and find out its deflection, and the stiffness turns out to be K into it is about 48 L cube by EI and so on, and the rotational spring you have to apply a unit torque at that point B and so on. I want you to get the concept, okay. You can handle many problems like this. Similarly, you can have cable suspended truss and so on. Let us take a very simple problem, okay. You have a cantilever, it is not a propped cantilever because a prop is elastic, you have a spring there of known stiffness K. How will it deflect? Well, these are the, let us say the force in that spring is x, and so the other reaction will be P minus x and the bending moment. So x is the single redundant, right. How will it deflect? Well, it will deflect like that, C may go down a bit and so on, right. And what will be the shear force and bending moment diagram? Something like that, clear, easy to draw. Now it will be interesting to find out how X is related to the spring stiffness. Can you guess?
K equal to 0, X equal to 0.
So if you had to plot K with X, how would this figure look?
K equal to 0, X equal to 0. And K is infinity.
Okay, so one point is here, you are right.
K is infinity, it is P by 2.
Will it be P by 2?
Oh, sorry.
K is infinity means you are dealing with this situation, right? Do you know the answer for this? Do you know the fixed end moment for a propped cantilever? We will need this again and again in future sessions, but let us go back to fundamentals. Let us say it is a fixed beam. Do you remember the answer for this? This is P, this is L by 2, L by 2. What are these fixed end moments? PL by? PL by 8. You can prove this by conjugate beam method. So remember, this is PL by 8 and this will be well, you need to take this beam, we will discuss this later, and reverse this moment, right. This is clockwise hogging. So if I apply a loading like this, then when I add up these two I get 0 moment there, right. But when I do this, it will take a shape, how? It will take a shape like that, right. And what do you think this moment will be? This is going to be how much? You have studied this? Okay, we will study it. This will be always half this value for a prismatic beam. Okay, so take it right now, we will prove it in the next class in a greater way. So you will find that whenever you have a kind of symmetric loading, this value will be always this value into 1.5. 1.5 times the conventional fixed end moment. So how much will it be? 3 and 60. And once you know this, you can find your reaction. How much will this be? Well, if this moment was not there, it will be P by 2, P by 2. So this is X. So it is P by 2, but due to the moment, this will increase and this will reduce by how much? This divided by L, that is 3P by 16. How much do you get? 5P by 16. So as K tends to infinity, you can't exceed this value, right. This value will be 5P by 16. How do you think this moves from 0 to 5P by 16? Some non-linear way. Can you generate an equation? So let us look at that. It is interesting to do these kind of problems. You can use the energy method. Remember, there are two energies here, one from the beam and one from the spring, just like we did the arch with a spring problem, and invoke the theorem of least work. Okay, do you agree to this equation? It is a straightforward equation. And let us assume you can do all these integrations. You see this part, you have to write the expression for bending moment and you expand it and you can solve it, and finally you will get an expression which is a function of this K and EI. So let us say K is lambda times EI by L cubed. In other words, I am trying to relate the spring stiffness with the beam stiffness. The stiffness parameters in the beam are related to EI by L. So let the spring stiffness be lambda times EI by L cubed. I have chosen lambda in a manner that it is non-dimensional. So it will be interesting to plot this relationship, and you will find the relationship is non-linear, as he rightly said. It will asymptotically hit the peak value of 5p by 16. For example, if lambda is 12, x turns out to be p by 4. So this is a complete way of understanding that spring type behavior. So it's somewhere, the actual behavior is somewhere between a cantilever and a propped cantilever. Let us take a more difficult problem, and we will stop this section with that. Let us say you have a hall, a room with a grid of beams like this. It is symmetric, okay, grid of beams. So you have one long beam from A to B and two shorter beams, and let us say they are simply supported. That means they are resting on pillars, they are non-monolithic supports. So assuming the beams to have identical flexural rigidity EI, which comes from their having the same cross section, same width and same depth, and zero torsional rigidity, which comes from the fact that they are concrete and concrete cracks easily. Analyze the grid system given that the segment GH is subjected to a uniformly distributed load of 100 kilonewton. Draw the shear force and bending moment diagrams of beams CD and AB. Now here I am only going to give you the concept, and I request you to go through the detailed calculation that at your leisure. It is all given in the book. So conceptually, how will you deal with this problem? It looks complicated. Separate out. So which one will you separate out?
CD and EF from AB.
Which do you think is supporting which?
AB is supporting
AB is supporting, or CD and EF are supporting?
all are interconnected. We can't say that.
Can't you say, or can you say for sure?
We can't say
See,
that.
GH is loaded. What's your hunch? What's your intuition?
Supporting CD and AB is supporting CD and EF.
CD and EF are supporting. CD and EF are supporting.
CD and EF are supporting because they are stiffer. See, the stiffer fellows will support the not so stiff beam. Can't you feel it? Ultimately the deflections are the same. So it does not matter. Let us say you made a mistake, it will show up with a negative sign in your reaction, but it is good to get it intuitively right straight. So this, do you think this is a good approach? That means I have replaced the connecting beams CD and EF with two identical springs, fine. And this is the loading, the GH is on AB, so I have to take out AB separately. Do you agree? This is perfect. Now I need a value of K. What is the value of K? K is the flexural stiffness of the beams CD and EF. So how do I do that? So both of them are simply supported beams. What's the span of the beam? Total, no? I am talking of CD, the ones that I am going to replace. They are 10 meters, right? 10 meters. So if I want to replace this with one spring, okay, I apply say some force F, this is going to deflect, let us say this is delta, let us say this comes down by the same delta. That's how I replace that entire beam with a spring, right? You see the power in this method. So is there a formula for delta that you can easily derive? What is delta? What is delta? You don't remember? That's right. So if the load is F, you should say F into 10 cube by 48, yeah, you are right. So K turns out to be F by, that is it. So you can do that, it does not take you much time, you have got that, and now you can analyze the beam. So your compatibility equation is the deflection at either G or H. Your compatibility equation is, let us say x1 and x2 are the forces at the bottom of the spring, the reactions, right. Obviously x1 is going to be equal to x2, right. So let us cut the spring at the base, let us see how much it moves. It should not move, there should be no separation between the cut ends. So your compatibility condition is d1L, that is the deflection here caused by this loading in the cut springs, plus F11 x1 plus F12 x2, this must be equal to 0. That is your conventional compatibility equation. You can work out all those quantities, and taking note of the fact that x1 is equal to x2, it reduces to that equation. So I will quickly show you how you can do that. You need to now find out d1L, F11 and F12, right. So your first thing is you need the bending moment diagram when x1 and x2 are 0 in the primary structure. That is easy to do, okay. You have a UDL, so you have a parabola in the middle and you have two straight lines, and those areas are easy to compute. Then you apply x1 equal to 1, that means you pull that spring down by x1 equal to 1, and you have a force in the spring, but you also have a bending moment in the beam, and that bending moment diagram is a linear diagram like that. That is what we call M1 diagram, and then you pull the other spring down with a unit load, you have M2 diagram, which is the same as M1 but laterally inverted, okay. So you have these diagrams. So can you not calculate d1L? What is d1L? d1L is the product of, comes from the product of this diagram and this diagram, okay, which you can work out, it is not difficult. What is F11? F11 is a product of this diagram with itself, F12 is this with this, F22 is this with itself. So these are simple things you have done before, but remember F11 has two contributions, one from the beam and one from the spring, because the spring also elongates, so the spring also moves. The spring movement is a value that you already know, okay. So you can work this out, you can write F11, F12 and so on. Conceptually is this clear, okay. You might encounter such problems in real life. When you simplify, you have a powerful technique to solve them, and you can plug in those numbers, solve for x1, and now once you know the value of x1, you see how it comes. You, let us say x1 is 45.83 kilonewton minus, which means it is compression. So you have a force acting here, and the same force acts downward on the supporting beam. Is it clear? And these diagrams are easy to draw. You can draw the shear force and the bending moment diagrams. This is complete. So all you had was one unknown x1 and x2 was equal to x1. You can solve this problem. So this is how you deal with elastic supports. Now straight away we will go to the last topic in this session. If you have tall buildings, you have a problem of both vertical load transfer and horizontal load transfer. So let us take a typical framed building like this. You have columns and beams. So can you see this? This is the framing plan where you have columns and beams, they are integrally connected, and the loads are transmitted from the slabs to the beams, to the columns, to the foundations, okay, story by story. It is simple to understand. This is vertical load transmission. What about horizontal load transmission? Well, it goes to the foundation through frame action. So you have to analyze this plane frame If you separate out the frames, you can do that. How do you do horizontal load transfer? Let us say wind is acting on the face of the building. You have cladding which will come in the way of the wind velocity. So there is wind pressure, you can calculate the wind force, the wind pressure will increase with the height of the building. Let us say you can work out those pressures, and you can find out, let us say, the force acting in an isolated frame at every floor level. How do you do that? Well, some people take just the wind pressure and multiply by the tributary area, that means half the width on one side and half. Well, that is one way of doing it. It works if your frames are all symmetric, but that would mean that your end frame, the last one, would take half the load compared to an intermediate frame. Do you think that is the way it is going to behave? Why not? Well, in reality that whole building is going to move as a whole. It moves as a whole because of the slabs being integrally present there. So the slabs serve a function not only of transmitting the vertical loads, but also is acting as a diaphragm. You know what a diaphragm is? It holds the structure together. So if you push one frame, the diaphragm as a whole makes sure that load is shared by all the other frames as well. Is it clear? Now if the building is not very long, let us say it moves together, that means all the frames are deflecting by the same amount at any particular floor level. Agreed? So if you replace them with springs, that means they all will take the same load. They all, because all the frames are identical, let us say. If all the frames have the same size of beams and columns, they have the same lateral stiffnesses. So they really take the same load. So if you have the total load F at any floor level, you just have to divide it by as many frames as there are. Supposing the frames are non-identical, then you will apportion the load in proportion to their relative stiffnesses. The stiffer frames will attract more load than the less stiff ones. This is some general knowledge. Now if you take out a plane frame, well, you have this longitudinal frame, you have to include the slab and the beam. Some people ignore the slab contribution, but the slab in compression actually helps the stiffness in the frame. So you call it a slab beam member. So this is a typical frame, but there are two frames, there are frames in the transverse direction as well. So when the wind is acting normal to the front face of this building, it is a transverse frame which will take the load. So you have to work it out. Let us take a simple problem, okay. Can you analyze this frame? This is a portal frame, it is symmetric, there is a load P, we discussed this earlier, that load will be shared equally P by 2, and that makes it statically determinate if this frame is symmetric. Remember we proved this earlier, and so this has a bending moment diagram as shown, drawn on the tension side, it has a deflection diagram as shown. The question I am going to ask you is, can you tell me what is that deflection in terms of P, or what is the lateral stiffness of this frame? What does it depend on? It depends on IB and IC, right? Let us say IB is infinity, that means you have a rigid beam. How much will that deflection be? The columns are flexible, columns will sway, but the beam will move like a rigid body. How much will it move? Let us say you isolate one of those columns, how will it look like? It is not a cantilever, the bottom you have a hinge. So can you make it look like this? So you see this picture, I have taken out the column, on top I put a spring, a rotational spring, okay, a rotational spring. If that spring stiffness is infinite, then when it sways, it will sway with the slope theta being equal to 0, but it will still sway, it will still sway. Now compatibility demands that the same theta is passed on to the beam. Now I can cut the beam at E at the middle, because that is where I have a point of contraflexure, there is no shear transfer, so I can put a roller there. So this is a clever way of simplifying the whole problem. Now the question is, how do I find delta? Well, let us take one extreme case where k is infinite, then can you tell me what the answer will be? Let us say theta is 0, how much will it move?
It's like proper.
Now it is a function of EIC by H.
P by 2 entire deflection.
How to find out?
PK deflection.
Be the same as cantilever with a.
That is right, it will be same as the cantilever. See, look at that picture, it is taken this shape. What is the force here?
P
So
by 2.
it is like a situation like this, right? This is P by 2, this is H. What do you think this deflection is? Is it so difficult? Huh? P by 2 into H cube by
3
3 E
EI.
I C. It is not difficult. You must be alert. Whenever you see a deflected shape like this, it should remind you it is like a hung cantilever. Is it clear? And the formulas are there to help you. So it is not that tough. You must develop the ability to write this down. And wait. Okay. The other point to note is, you also know an expression for theta, right? If you have a simply supported beam of span L by 2, do you agree that the relationship between the moment and that beam, let us say I have a beam, elastic beam, and I apply some moment here, say m naught. This is going to rotate like this. What is the relationship between these two angles? Do you know? This is twice that, okay. And what is this relationship? Theta will be m naught L by 3 EI, right. So that is what we have done here. So you have these relationships. So you have an expression for theta, and if you take the rigid beam idealization, do you agree to this cantilever action of the moment of the column, you get delta naught equal to this quantity which we just derived, right. Now let us say theta is not equal to 0. In reality it will not be equal to 0, because the beam is not infinitely rigid. Beam has a finite stiffness EIB by L. Then what is the additional deflection that you have? So delta will be delta naught plus what? Rigid body rotation. So how much will that be? Theta into theta into H. You must think like that. If theta is not there, you have delta naught. If that spring is finite, you have a rotation here. It is a rigid body rotation. So rigid body rotation. So you have, it is as though this rotated by an angle theta, and so you have an additional movement here which is theta into H. So that is a clever way of simplifying and breaking down and understanding, and you can do that, right. So you have a nice expression. If you simplify it, you can write an expression for delta, you have a value of theta, and if you bring in a stiffness parameter which we have introduced earlier, EIB by L to EIC by H, then you can write an expression for K. This is not very important, okay. I just want you to get a general sense of how we can simplify things, but I want you to remember the limits. So you can write K in terms of gamma, and you will find that the maximum value will be 6 EIC by H cubed, which is when the beam is infinitely rigid. If the beam is infinitely flexible, you have a problem, the system becomes unstable, because you have two internal hinges there and you have very large deflections, it will not survive. So is this clear? So this is one typical extreme problem. Let us take the same portal frame and fix it at the bottom, okay. This is now statically indeterminate. Earlier it was hinged at the base. Now let us begin with the rigid beam idealization. This building is sometimes referred to as a shear building, okay. It's a shear mode of movement. Now you see how it is going to behave. If IB is infinite, it will just slide horizontally, and this is fixed on top, fixed here, it is kind of guided roller here, guided fixed. So the slope there is 0, the slope here is 0. Do you agree that this point of contraflexure will be in the middle? Do you also agree this P, that these two columns will move identically? They will have the same bending moments and same shear force. Do you also agree that this load P will be shared equally by the two columns? Now can you give me an expression for delta naught with that knowledge? Okay, look carefully. Can you give me an expression for delta naught in terms of P, E and IC and H? Please work it out. See, this is how you check. Let us say someone in your structural engineering design office comes up with some value, you should at least make sure the value makes sense, it should lie within appropriate bounds. So this is one extreme. Your actual deflection will be more than this. This is the least value of the deflection you can get when the beam is infinitely rigid. What is that formula for delta naught? Okay, where that hinge is located, what is the movement? So look at the isolated model. It will move by delta naught by 2, right, in the middle. You see here, if this overall movement is delta, do you agree this is delta naught by 2?
Yes, sir.
Can you write an expression for delta naught by 2? That is easy, that is a cantilever, right, and it is 2 times that. So is it okay to say that delta naught is this into 2, where this is P by 2 into H by 2 the whole cube by 3 EIC? It is the same formula except I am taking half the height now. Is it? Because of parity, because if you flip it upside down also it does not change. It is like the settlement of supports problem. Let us say I had a beam like this fixed here, right. Let us say I push this down. So what is a deflected shape? Let us say this is a chord rotation. The deflected shape will be 0 slope there, goes down like that, goes down. Okay, right. Now does it matter whether this goes down or goes up? Can't you feel that the point of contraflexure will be bang in the middle if it is a prismatic beam? Imagine this goes down. So these are all reversible. So this point of contraflexure will always be in the middle of the beam, right. You keep moving it up and down, this chord rotation is going to be like that, and if this is delta, this has to be delta by 2. You are not convinced? Okay, let's say you move it up. Let's say you move it up. What will be the deflected shape? Right? The bending moment diagram for this is going to be like this. Bending moment diagram for this is going to be like this. Right? Now when I add up these two, what should I get? I should get 0, the beam will be flat. Agreed. And I can flip it over. I can flip it over. Right? So it does not matter. So we talk of chord rotation, it is not whether the right support goes down or the left support goes up. You have a clockwise chord rotation here, which we call phi. You have an anti-clockwise chord rotation here. The points of contraflexure will always be in the middle. And let us finish it because we need this knowledge later. Let us work it out. So let us say this force here is P. Equilibrium demands that this also is P, right? And what do you think this deflection is? Delta 2 will be P into L by 2 the whole cube by, it is a small cantilever, right? I can cut it there, by 3I. It is a clever way of solving the problem. So this turns out to be, remember this is PL cubed by 24 EI, or you can say P is equal to 12 EI by L cubed into delta. So you have a relationship between this delta and this P. It is very important to remember this relationship. Now what is your moment? You get a moment here with acting down, so you have shears acting down and up. You have a moment here. You also have a moment here. What are these moments going to be equal to? P into L by 2. How much does it turn out to be? P into L by 2 is how much if P is this? So it turns out to be, the moment is 6 Ci by L squared into delta. These are very important formulas, 6 Ci by L squared into delta. So the summary of what we have done here is, if you have a clockwise chord rotation, okay, you can also write this as 6 Ci by L into chord rotation phi, because phi is delta by L, assuming delta is very small compared to L. Is it clear? So if I have a clockwise chord rotation, I get a constant shear force like that, whose value is 12 EI by L squared into phi, and I get equal moments on both sides in the same direction, in this case anti-clockwise, of 6 Ci L squared, 6 Ci by L into phi. Is it clear? Now even if you forget these, you can derive these, they are not very difficult. So I hope you understand when you come back to this how we got an expression for delta naught. Is it clear? Now this is the stiffness that you get, it is called the translational stiffness of a shear building when you push it horizontally, you get this much deflection. Now in reality the beam is going to bend, okay, and it is a little difficult to work out that formula, but let us take the other extreme. Let us say the beam is infinitely flexible. Can you draw the deflected shape for that? Now it is not going to be unstable if you put internal hinges there. So how much will it move if it is infinitely flexible? So this is a bending moment diagram. Can you see for this particular case, this is P, this is P by 2 into H by 2 is PH by 4, so you get typically bending moment diagrams like that, okay, and K has a value of 24 EIC by H cubed. Let us put hinges. How does it behave? If you have an infinitely flexible beam, how will the columns behave? Simple cantilevers. So that is easy to calculate. If you do that calculation, you get PH cube by 6 EI, and your bending moment diagram will look like that because your beam will have no bending moments, right, because you got hinges there. So it is very interesting. I have looked at all the extreme cases. The summary of this, so here it turns out to be 6 EIC by H cubed. So take a portal frame, a symmetric portal frame, take the base as hinged, your horizontal stiffness is going to vary between 0 and 6 EIC by H cubed. That is what we saw in the previous slide. Fix the bottom and it is going to, the minimum value will be 6 EIC by H cubed and the maximum value will be 24 EIC by H cubed. So when your beam is infinitely rigid compared to the infinitely flexible case, the stiffness of the whole frame gets magnified by a factor of 4, okay. So you, the sum and substances you can write in terms of lambda, finally it is between 6 and 24, okay. Now the whole idea of doing this is to tell you that when they first started building tall buildings, tall frames, they found it very difficult to manually analyze these highly indeterminate structures. So they took shortcuts, okay. For gravity loads they use a concept which we will see a little later called substitute frame method, where they just took one floor and they assumed that the columns were fixed at top and bottom, so it was much easier to analyze. The argument was whatever happens far away from this story is not really going to affect that floor. It is a hunch which works out well, you can prove it with Mueller-Brislow's principle. When it came to lateral load, it took some time for them to work out a simple way of cracking the problem, and they came up with a brilliant idea. They said, let us make some assumptions and make that whole frame statically determinate, okay. So some methods evolved over centuries and they are still popular today. How do you convert, and I want you to give me the ideas, how do you convert an indeterminate frame to a statically indeterminate for the sake of approximate analysis. Now take a look at this. At this point I want to convey, at the bottom engineers often have this worry about, should I model it as a pinned support or a fixed support? When do you model foundations as fixed and when do you model them as hinged? And the reality is somewhere in between often. When is it hinged? When your foundation can rotate. When can it rotate? Well, when you have a shallow foundation, when you have isolated footings, and even sandy soil, when your safe bearing capacity is not very high, because even a small movement there will release whatever moment you calculated. So that is one extreme, okay. When do you model it as being fully fixed? Okay, when let us say you even have an isolated footing but it is resting on very hard strata, there is no way the rock is going to rotate, okay. Or you are on piles and the piles have a pile cap which is heavily interconnected, okay. So in such cases you can go for a fixity, but the spring shows you can handle all conditions in this situation. Now one thing you can notice, I am now taking one type of frame only in this session. Let us say the frame is single bay means just two columns in one story but multi-story, single bay multi-story frames, and let us say that it is symmetric, which is what it normally is. That means all the columns on one side are the same as the columns on the other side. If the wind is acting from left to right, you call these columns as windward columns, and these are columns are referred to as leeward columns, right. Now because the frame is symmetric, you can assume this to be made up of two loadings, one is symmetric, the other is antisymmetric. Just divide P1 and P2 by 2 and put them equal and opposite here, and then put them here on the same side. So this is called an antisymmetric loading, it is called symmetric loading. When you add the two, you get back the original loads. There is a great advantage in doing this. The advantage is this part, the symmetric part is very easy to calculate. You end up getting axial compression in only your beams. Will there be any deformations? No, you are assuming axial deformations to be negligible in frames. So the first part you can practically throw away, and so all the bending moments, all the curvatures, all the deflections are coming from the antisymmetric component. It is very interesting. Not only that, you will find that there are points of contraflexure always in the middle of the beams. They have to be in the middle of the beams because of this kind of behavior. When you, whether you push it to the left or right, your behavior will be the same, right, and all the columns are moving in the same way. So you will have points of contraflexure always in the middle of beams in such frame, in symmetric frame, but in the columns they could be anywhere. So that is the other issue to note. Windward and leeward columns at any story level deflect identically, they share the story shear equally. Now let us understand the meaning of story shear. So we are saying this hinge, I mean it is not a deliberate hinge, it is just the fact that the bending moment there is changing sign, is going to be in the middle of the beam, but this hinge could be somewhere in the middle of the column. We have not yet proved that it is exactly in the middle, and similarly this hinge in the lower story is somewhere. Supposing the bottom is hinged, then this point of contraflexure will actually shift to the bottom. Is it clear? So we do not know where this is, but one thing we know for sure, we know that this hinge and this hinge will be located at the same height. Do you agree? This hinge and this hinge will be located at the same height. Now let us say I cut a section here along this, wherever the hinge locations are in the columns, and I take out the top part, then it is like a cantilever, it is taking some lateral load, that is referred to as a story shear. Look at the word, story shear is the lateral load taken by all the columns in one story. So if your load here is P2, the story shear in the second story is P2. Now if I now cut a section at the lower story, then the upper story is part of that section. What is my story shear? If I cut a section here, it will be P1 plus P2. So you will find the ground floor columns take more shear than the upper story columns, so they will be loaded more heavily. And can you realize, so the point made is this story shear will be shared equally by this and this story shear will be shared equally by this and this. With that assumption we can solve this problem. We will stop here and we will complete this very interesting simplified analysis in the future. Thank you.